Thank you so much for coming. It's wonderful to see so many people here. I'm Tsu-Jae King Liu, the Dean of the College of Engineering, and it's my pleasure especially to welcome back many of our alumni and, of course, the parents and students who are currently here. So this morning, this session is to give you some highlights from Berkeley Engineering, showing you how we are actually innovating to make a tremendous impact on our world. As you may know, Berkeley engineers have advanced to forefronts of knowledge and creativity to innovate new solutions that will solve some of the world's greatest challenges. And we do this because we really want to make an impact, a positive impact, to shape a better future for all of us. So today we have three Berkeley Engineering faculty members. First of all, we have Pieter Abbeel. He's a professor of electrical engineering and computer sciences. And his area of expertise is in robots and deep learning. So he's the director of the Berkeley Robot Learning Lab and also the Berkeley Artificial Intelligence Lab. So he'll speak first. Second, we have Matthew DeJong, and he's a professor of civil and environmental engineering. Matthew's area of specialty is in assessing the resilience or the structural integrity, especially of historic structures, to preserve them. And then third but not least is Professor Grace Gu from mechanical engineering. Her area of expertise is in smart additive manufacturing. So in other words, using artificial intelligence to improve manufacturing methods. So what we'll do is I'll give each of the faculty members some time to give you a 10-minute presentation to introduce you to their research, and they can tell you about the exciting things about their area of research. So they'll come up and spend 10 minutes each, and then I'll ask them to come up together as a panel to take questions. Okay? So without further ado, I'd like to invite Professor Pieter Abbeel to the stage to tell us about his research on robotics.
Thank you, Tsu-Jae. Good morning, everyone. What I'd like to do is share a little bit with you what are some of the latest trends and advances in AI and robotics. One of the things you might already have seen in the news a couple of years ago is headlines like this, like Stephen Hawking warns AI could end mankind, or Elon Musk essentially saying the same thing. And then you might see headlines saying the exact opposite. Even what Elon Musk and Stephen Hawking say, don't believe it, it's not true. It's complicated, but there's a lot of action in AI. For example, you look at the strategic plans of countries. More and more countries have strategic plans specifically centered around AI and how investments in AI could advance their economy, their military, their healthcare, and so forth. Life as a professor in AI actually completely changed in the last few years. So before 2015, life was really very quiet. Just sitting behind a computer, doing some emails, meeting with some students, reading some books. But then since 2015, everybody got excited about AI. And so, for example, here's a picture from just a year ago, having dinner with Jeff Bezos from Amazon, who invites 100 of the leading AI scientists to Palm Springs to learn more. Similarly, in the last couple of years, worked with Elon Musk, actually met with the King of Belgium to brief him on AI for a whole morning. Bill Gates, Larry Page, Jensen Huang, and so forth. And this is our conference now. About 8,000 people, and it's all just math and algorithms. There's really nothing that particularly entertaining, but somehow it actually sells out in less than 12 minutes these days. So it's much like pop concerts where you got to refresh at all times if you want to make your way in. Now, here's the craziest thing. Here's a painting made by an AI system, sold at Christie's for almost $500,000. Now, the even crazier thing is, the AI system is essentially this equation over here and is a signature. That equation was invented by a PhD student at University of Montreal a few years ago. Then, a year or so later, somebody else writes the code and puts it on GitHub. Then, yet another year later, somebody else downloads the code, runs a marketing campaign, and sells it. So the person who made the money of this did not invent it, did not even write the code. They just ran the code and managed to do good marketing. So some hype around all of this, for sure. But actually, a lot of fundamental advances are being made. And so what I want to do here with you is highlight some of those advances and give you a little bit more understanding of what's actually happening, what's becoming feasible. So, what is AI, and what are the driving forces behind it? Let's start with something very simple. Look at this picture. everybody knows it's a coffee mug. Very simple for us. But imagine you need to write a computer program to understand this is a coffee mug. What are you going to do? Well, what does a computer program see? It sees a bunch of numbers. So how's it going to make sense of those numbers? If this number higher than that, then it's a coffee mug. Very hard to do. In fact, nobody succeeded. But instead, as it turns out, recently people succeeded, instead of trying to directly program this, to learn the pattern. More specifically, to lay out a large neural network, and this is a tiny neural network that fits on a slide. Real neural networks are, instead of 100 neurons, maybe tens of millions of neurons, lay out a large neural network that takes in an image, processes it, and outputs a decision as to what's in the image. Each neuron in the network is very, very simple. It just takes in some inputs, takes the weighted combination of them, and outputs the result. But it turns out if you put enough of them together, they can do something really complex like recognizing what's in images. Now, how does it recognize this is a dog versus a cat? It depends on the strength of the connections between the neurons. You need to wire this up correctly for it to recognize it's a dog. And so now the question is, how do you wire this up? Is that going to be any easier than just writing code? Well, it's actually really hard to wire this up by hand. But what you can do, you can actually train it by examples. So you collect enough example images, and you feed them in one at a time. Feed in a dog. Initially, the network is wired the wrong way. It might say cat. That's okay. You then do a backward calculation in the network, fix up the wiring, and now it'll know that's a dog. Feed in the next image, repeat, 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 and after a few million images, something magical starts happening. It actually starts recognizing what's in an image, even images that it's never seen before. You might wonder, how much of progress was this? Well, there's a big competition called ImageNet. And in ImageNet, the organizers have secret images. They don't share with anyone. And you send in your computer program, and they run it on the secret images and evaluate how many errors it makes on recognizing what's in an image. The winner in 2010 had about 30% error rate, not much better in 2011, 2012. Traditional computer vision was stuck. But by training deep networks, it was shown that you can halve the error rate. And not only that, it wasn't a one-time thing. People realized this method works better, switched approaches, and from there, actually, was a rapid acceleration in progress. And by now, this competition has been retired because human-level error rates have been achieved. Now, this is in computer vision. The exact same thing happened in speech recognition. Traditional approaches of trying to more directly program what it is that you hear were not really making much progress anymore. Training deep networks went right through that. Same thing happened in machine translation. You collect a bunch of sentences, pairs of sentences, one in English, one in Chinese. Enough of those pairs, the neural network learns the pattern to go from one language to the other language. Really, what's happening under the hood is a change in programming paradigm. So traditional programming is all about writing lines of code. It might look something like this. And it might work well for classical things, but for AI applications, this doesn't really work. Instead, people switch to a new type of programming where they say all we have to do is lay down a large neural network. If the network is large enough, it can represent any pattern, but will it represent the right pattern? Well, that depends on the data you feed in. And so now programming becomes almost an exercise of collecting data and feeding in the right data, the right input-output pairs, such that it starts recognizing the pattern you want it to recognize. If it doesn't yet, you go collect more data, repeat. So what I showed you so far is deep supervised learning. Deep refers to the fact that a large neural network is being trained with many, many layers, so very deep. Supervised means that the way it's trained is by providing examples of input and output pairs. And you give enough examples, it'll start recognizing the pattern. And that really works, actually, and you can build applications around this. What are the new frontiers? Where's the research happening now? That's in deep reinforcement learning and deep unsupervised learning. What are they? Well, imagine you want a robot to do something. You don't just want pattern recognition and say, oh, dog, cat, and so forth. You want something that can actually close the loop. Take an action, see what the result is, repeat to try to achieve goals. Can we do that? Can we have an AI that learns to achieve goals? Actually, you might have seen it in the news. AlphaGo from DeepMind was able to learn to win the game of Go against the best human players. How did it learn that? Largely by just playing against itself, practicing over and over and over, and gradually becoming better through its own trial and error. While DeepMind was working on deep reinforcement learning, what this is called, for games, both board games and video games, at Berkeley we're working on deep reinforcement learning for robotics. So can we have this robot learn to run on its own? Much like a child. A child, you don't have to tell it exactly what running is, you just let it try, and over time it'll figure it out. Can we do the same thing with a robot? And we actually haven't seen any learning in action yet here. All we've seen is me telling you about great results achieved by learning, but we've never watched it happen. So what do we think is going to happen when learning is in progress? Initially, the neural net is randomly initialized, so it's just going to fall over, because most random things will not succeed. But it'll randomize a bit, and one of those times it'll fall over just a little bit later. And when it falls over that little bit later, it'll reinforce that through backpropagation, change the wiring of the network to make that more likely to happen again. That's one iteration. And iteration after iteration will improve the network, and let's see what happens. So initially it falls over, but then after 10 iterations it falls over just a little later. And after 2,000, it's figured out running. And the beauty here is that the same piece of code can be used to train any type of robot. You don't need to write new code to train a new robot. You just run it on the new robot, and it gets trained to do what it's supposed to do. This was in simulation. How about real robots? Here is Brett, the Berkeley robot for the elimination of tedious tasks. Brett lives on the 7th floor of the AI lab at Berkeley. And here Brett is learning to put the block into the matching opening. And actually figures it out in about an hour of practicing. Now, first you might say, that's a long time. You can do it on first attempt. I think most of you can. But think about it. This robot's starting from scratch. It's not done anything else before. You've done so many related things before, so it's not totally new to you when you try to do this. In fact, you might have done this as a child. But this robot's starting from nothing, and then figures out the vision system and control system to succeed at the task. From there, we actually started a collaboration with NASA on controlling this robot. It's kind of a crazy robot. It's called the NASA Super Bowl. It's supposed to do planetary exploration. You might wonder, why not a car-like robot? Well, there are some reasons for this. This can be put into a smaller package. And so it's a bit like a tent. When you package it up, it's small volume in your rocket. Then when you expand it, it's big, and that's what you want. Because when it's big, it's like a sphere. And it's like having wheels in every possible direction at all times, so you can move in any direction at any time. Turns out very hard to control, and so traditional control did not succeed. We ran reinforcement learning, and it learned to control itself. So that was reinforcement learning. It's about learning to achieve goals from your own trial and error. And actually, the analogy you've probably seen in your own life a lot is dogs. When you train a dog, essentially the dog is doing reinforcement learning. You don't get to tell it what to do. You just get to say good dog, bad dog, and it has to figure out how to achieve the good dog outcome and not the bad dog outcome. How about this unsupervised learning thing? Why do we care about yet something else? It feels like we covered it. We've seen how to recognize patterns. We've seen how to learn to achieve goals. What else is there? Well, you still need to supervise. Supervised learning, you need to provide data that's input and output pairs. In reinforcement, you need to say good dog, bad dog. You need to supervise in terms of whether it's achieving the goals or not. Can we learn just like that? Just like babies look around in the world, and then they learn about the world from just being on their own, looking around. One way to maybe do this is to flip the script. For now, we've looked at going from image to a decision. Can we flip it? Can we go from some random input, like was done for the painting, and generate an image? In code, it's very easy. You just change the dimensions of your code, and now the network goes from small to large. Let's see what it generates. So we put in a random code, out should come an image, and here's what they look like. They're not really great images. But the question is now, can we train it? Can we train the network to generate images that look like real images? Actually, we can. And here's the training in action. So what you see here is gradually over time, the network is getting trained to generate more and more realistic images. And for any random code you feed in, you get a realistic image coming out. Now I can hear some of you thinking, realistic image coming out, not so realistic. And that's true. I mean, these are 16 by 16 something images. It's very coarse. It's not exactly the kind of dog that you'd see in real life. It's a little more approximate. But you can recognize some dogs in there if you squint, and there's some cars and some boats. And this is 2016. Now, a couple years later, scaling this up and a few more tricks in the book to make this work even better, here's what we get. So these are all automatically generated. You feed in a new random code, you get a new face out of somebody who doesn't exist in the real world. In fact, you go to this website, you refresh, you get a new face. So you want a new profile picture, that's not you. You can just go to that page. You're not stealing anybody's picture. It's nobody in the real world, and you can just put it up. Now, one of the things that's pretty exciting in my colleague Alyosha Efro's group, one of the students said, you know what? If we can generate those things, maybe we can generate things that make me look really cool. So, actually, a question. Who here is pretty good at dancing? Can you do a raise of hands? So one person's really good at dancing over there. Okay, so you are the star here. But all of you can also become stars online, it turns out. So Tingwei said, what if I just make a fake video of myself dancing? Can I do that? Because then everybody will think I can dance too, and that might be cool for, getting good recognition from other people. So he said, okay, let's do it. This is just a calibration. Top left is the source video. So this one is real, but Caroline and Tingwei can't dance like that. That's all fake. Now, maybe not everybody likes hip-hop dancing. Maybe you want to make a better impression by ballet dancing. We can do that too. So let's switch it over. Here we go. Very simple calibration. Everybody should be able to do that simple calibration. And look at the realism. This is all fake, but look at even the shadows put on the wall behind it, on the glass behind it. You can do the same thing for text. You can train something to learn to generate text. So it's been trained on much text on the internet, then it's given a prompt, and here's how it completes it. This did never happen, but it's a story that reads like a real story. Something got stolen, there's some kind of thing about some administration official saying it's a really big deal and never going to let it happen again. They're going to take action right away. It's exactly what you'd expect in an event like this. In fact, it's so good, OpenAI decided not to release the tool that generates this to avoid people generating a lot of this kind of fake news. Now, what we covered here is kind of a breakdown of the three main thrusts that have led to the most advances in AI in the last 5 to 10 years. It's all deep learning, but within deep learning, there's deep supervised learning. It's about input-output, and that really works. You just collect enough data, have one expert work on it, it should work. The frontiers are reinforcement learning, learn to achieve goals, and unsupervised learning, learning from unannotated data, for example, generate images, text, and so forth. Now, you might wonder, can I learn more past this session here? If you want to learn more, I'd recommend you subscribe to this newsletter over here. This newsletter by Jack Clark. He used to be a reporter at Bloomberg, doing the AI beat there. Now is communications director at OpenAI. Every Monday, you get an email in your inbox, and it summarizes the last week of progress in AI, commercially, politically, technologically. 2-minute skim, and you know what's been happening. If you want to dive deeper, and you could come and study at Berkeley, you could already be here, but many of you might not have the time to come and study at Berkeley again. So here are a few things you can study from home. So if you really want to learn this and become one of the world-leading experts, once you have a bit of background in linear algebra, computer science, and probability, you will be ready to study these 7 classes. And after you study those 7 classes, you'll be good to go. And maybe you can join my lab and we can work together. Thank you.
Good morning. I am a civil engineer, earthquake engineering by training, so my background is in earthquake engineering. Still, a lot of my research is in earthquake engineering, but this morning I want to talk to you about something else, which is monitoring and modeling of existing structures. So, while many things are advancing very quickly, and you saw some nice demonstrations just now, our civil infrastructure is around naturally for a long time, and it's very hard to replace. So while we're making a lot of progress in new designing new buildings, new bridges, we have a huge problem on how to maintain and manage what's there and what's going to be there for a long time. So our goal is really, how can we better model and particularly monitor? How can we use data to better maintain what we have and what we're going to be left with for a while in reality? So I'll show two examples, one related to tunneling and one related to rail bridge degradation. So previous to here, I've been at Berkeley for 1 year. I was a faculty member in Cambridge University for 9 years, and we were involved in a lot of infrastructure projects. One of them was this. This is the Crossrail tunnel, which goes under London. So this red line represents twin tunnels bored directly beneath all of London. Here's a profile beneath the city. And basically, there's a huge problem related to settlement and assessing all of these buildings on the surface for settlement issues which need to be mitigated. And so first we did some work in the laboratory, and this is the centrifuge, an experimental facility in Cambridge. This is a very large beam arm, 10 meters, and there's a little bucket here on the end. Essentially what we do is we build a model in that small bucket, we spin that thing very fast, we create an 80 G gravity environment in that little bucket, and what that allows us to do, it allows us to build a scale model of a structure or a tunneling scenario at 1/80th scale and represent the correct kind of stress strain conditions of the real scenario. So in that bucket there, we're building something like this. So we're building this container. There's the soil. In there you can barely see our model tunnel. Here's our building, which we 3D printed, and this is it here. And if you look in cross-section, there's our tunnel. So we're extracting fluid from that tunnel, and what that does is it simulates the settlement we get at the surface of the ground, which then causes the damage to the structures at the surface. So we're simulating all this in the laboratory, and this might not be so exciting, but we get data like this, which I think is extremely impressive, because this is, if you see in the laboratory scale, this whole profile of settlement at the surface is sub 1 millimeter, and we're getting all of that data from photo images. We take those images, we use those images to measure the settlement profile at the surface and through the soil, and that represents the settlement of the real building would be 80 times that in the field scenario. So it's very hard to do an experiment like this at full scale in a city, whereas we can do this experiment in the lab in a very precise and controlled way. And the benefit of this is then we can train or we can validate our computer models. So we're sure that if we can simulate this right, we have a much better chance of simulating that scenario at the real scale. So that's kind of what we did in the laboratory, but then we did a lot of field experimental work as well. And fingers crossed if this demonstration works correctly. I'm going to show you really quickly how we do some of the field monitoring. So I figured we won't look at slides the whole morning. We'll just do one real physical demonstration here. So right here I have a system that we're using to monitor buildings in the field. And what this is the analyzer. There's a cable from there, a fiber optic cable, and then that fiber optic cable is attached to this. And what this system essentially does is it shoots a pulse of light down the cable, and then as you stretch the cable at every point, some of that light is backscattered back to the analyzer. And depending on how much you stretch the cable at every point, you get a different characteristic of the light returned. So what it allows us to do, essentially every millimeter along this cable, we have essentially a sensor that we can measure strain or stretching. So you have 100 sensors. Each sensor essentially measures at 250 times per second, so 250 hertz. So we get 250 measurements of strain at every millimeter along the cable simultaneously, which is pretty cool. So that's what's happening in the background behind me. So if I bend this like this, whoops, that was too far. You see the profile of the strain on that cable on one side changing. That's nice, and we can do that, but I'm very interested in dynamics, being an earthquake engineer. So if you want to monitor the dynamic response of a building or bridge or something, you can measure at multiple points dynamically as well, which is kind of useful. So we didn't, we didn't directly develop this technology, but what we've done is we've done a lot on applying this in the civil engineering field, and a lot on how we can then coat these fibers, treat these fibers so we can embed them, for example, in concrete. It can be a passive sensor which lasts for a very long time. That fiber optic sensor is embedded in our structure. Anytime we want to measure, we can just come and plug in our measurement system and detect what's happening in the building. The nice thing is the technology is all in this box. So as technology progresses, we have a sensor which is increasing its performance and capability along with the technology outside, because all that's embedded is a fiber optic cable. All right. That worked well. So how do we do this in the field? So here's an example again from London. This was a project we were involved in, which was a subway expansion. Everything in blue and purple. This is a plan view from above. Our new tunnels that were developed. And I'd just like to highlight the two buildings, the yellow ones, which were above this tunneling expansion. And they were very worried about these buildings. First, because Mansion House is where the mayor of London lives. And second, I won't show you any data on that one, but St. Mary Ab Church is a very old building. As Tsu-Jae said, I'm also very interested in historic buildings and how to preserve them, but they were very worried about this because this is a Christopher Wren building, famous architect in London, listed important building. So we basically wrapped this building with fiber optic cables, which you can see in green here. And then also a lot of other traditional types of sensors. And then as the tunneling progressed underneath, which is right here, we get real-time measurement of localized strain all around the building. So we saw actually cracks developing, and now the building owner likes that because they're definitely sure of the impact of the tunnel on their building, which is important to them for basically getting some money back from their insurance company. But I think this was a very good demonstration of the power where we can measure locally the damage, whereas with traditional sensing, this is a bit more difficult. One other way we measure this in the field, we worked with people at JPL, Jet Propulsion Laboratory in Pasadena, who do a lot of work with satellites, and we're interested in measuring on a bigger scale the effect of tunneling and how the ground moves due to that. So this is again a picture from London. This right here, that red line, are the tunnels I showed you earlier. But that is all data, and here's a zoom in of one point on that red line, from all different buildings, where the satellite measures differential settlement. So one satellite passes, measures where the building is, another satellite passes, measures again, and so you can slowly see, with every pass, how the buildings are moving. So each of those dots are specific locations on buildings. You don't have to put anything there. They just detect the natural features of the building and see how the ground moves. And so here you see an example of this cluster here where you got 30 millimeters or 3 centimeters of settlement, which is quite significant if it's differential for a building. It causes cracking and things. So if you don't have a building which you can afford to monitor in precise detail, you can do this at a much bigger scale to understand how things are moving. So that's another project we've worked on. The second topic I'd like to discuss is degradation of rail bridges. And this involves dynamics, which is something that I enjoy working on. And it's a big problem in the UK, but also in the Bay Area, around the world, on how we assess old bridges and their performance. And in this case, we have a very old bridge that's not in very good condition, with lots of cracks, lots of previous retrofits, and it takes the East Coast Main Line, which is one of the main train routes in the UK. And the question is how do we ensure that this bridge with all these cracks in it is performing satisfactorily? And so again, we've used this method of fiber optic cables to attach to the bridges, and here's just an example where we're stringing and now attaching on the exterior these cables. And from that, we can monitor, again, behavior at several points. The benefit of this is we have upwards of 80 or 100 point locations that we're measuring, and we only have one measurement box and one cable. If you want to put 80 sensors on a building and wire them all separately and do all your data acquisition and everything else, you have a huge mess of cables, and really it's not very feasible. And so what this allows us to do is detect very early if there's local degradation that might be of concern at any point. So the examples I've shown were smaller scale. The nice thing about fiber optics is you can measure up to the kilometer scale, so you can string fiber optic cables for up to several kilometers and detect strain all the way along that. So for long linear infrastructure, which I have some colleagues, we've worked together on this as well, like dams, embankments, rail, different things like that, telephone wire, you could potentially use this technology to measure very long distances where it's hard to put point sensors at a lot of different locations. So here's an example of the installation there. It's all remote, so there's a cabinet with all the information in there, powered by solar panel. Every time a train comes across, the system turns on, takes all its measurements, sends all the data, and we can access it from here in Berkeley, so we can do the analysis and the change detection on how the bridge is actually performing. This data also goes directly to AECOM, a large industry contractor, and Network Rail, who manages the bridge, so they can also understand how their bridge is performing. This is just one example where we can measure and detect new crack initiations. So we saw over time, this is a very simple image to show increase in response. And sure enough, you go to site and identify and mark out the new cracks in red on the underside of the bridge. So you get an early warning of that behavior. Finally, just to close, I also, as I said, I have a passion for historic buildings and have done a couple of projects on trying to design new buildings or structures, shall we say, using historic methods. This is a stone vault, 300 stones, each approximately a meter big, completely unreinforced, but in pure compression. So no reinforcement, just stacked stone. And this was built at the Venice Biennale in Venice. And I think it's a demonstration on how computational tools can be used to create aesthetically pleasing structures, but using very simple methods. This was led by an architect named Philippe Bloch, but we did the engineering design for that. And I'll close with that. Thank you.
Good morning, everyone. My name is Grace Gu, and I'm currently an assistant professor here at UC Berkeley in the Department of Mechanical Engineering. I'm very excited to share with you my research on engineering the next generation of materials using additive manufacturing and artificial intelligence. I'm going to start off my talk talking about cracks. Cracks can form everywhere, from our cell phone screens when we drop our cell phones, to windows, and to the walls around us. Now, the dangerous part about cracks is that they may start off very small, but over time, they can propagate, leading to catastrophic failure of the structure. An example is shown here from a very deadly airplane crash in 2002, where it started off with a very small crack in the tailpipe that nobody saw. Over 20 years, this really small crack, very unseen crack, actually spread like a spider web, shown in this picture at the very top right. And this spiderweb crack spread around the fuselage. And eventually, the airplane actually disintegrates. Shown here. I have dedicated my entire PhD trying to understand cracks, how they form, why they form, and how can we develop better materials to prevent them from propagating and from forming in the first place. The material property associated with how resistant a material is to crack propagation is called toughness. And it turns out that nature has many great insights on how to create. Turns out that nature has many great inspiration on how to create tough materials. Natural materials such as seashells and bone are composed of soft and stiff building blocks. You can think of a soft material like rubber, and you can think of stiff material like glass. And the unique combination of them together creates a very tough material. And it turns out that adding a very soft and a weaker material to a very stiff and very strong material helps to alleviate stress concentration and helps to trap cracks from growing. This is what nature does. In our research, we look into mimicking the biological architecture seen in nature using models created by computer-aided design. This is an example of a model that we have created that's inspired by seashells. Now, what we do then afterwards is that we translate this virtual model into a physical sample by using additive manufacturing. And this is a multi-material, a very advanced 3D printer that can print two materials simultaneously together, helping us to create this bio-inspired prototype. An example of our prototype is shown here. You can see that with 3D printing, it allowed us to create a material that's made up of two materials, or termed as a composite. And it helped us to create a material that it has multiple layers as well. Now, we have got to this point where we created this prototype using 3D printing. Now the question is, how does it perform? Is it any good? Could we potentially use this kind of material for, let's just say, helmet designs or body armor? And so what we want to do is that we actually test this prototype. And we clamp the prototype between constraints, and we drop a weight onto it. And we want to see how it performs. And we first test a very simple geometry, one of the stiff constituents of what the material is made up of. You can see when the weight is dropped, the sample completely shattered. It failed catastrophically. And next, we're going to test a bio-inspired geometry from seashells. And you can see here that when the weight dropped, it actually rebounded, leaving very little damage on the sample itself. And we drop both of the weights at the same velocity on both of the samples. And I often joke, if you had to choose the type of armor you would wear, which one would it be? And we didn't just test against this very simple geometry, we also tested against many other composite geometries as well. And this bio-inspired geometry outperformed all of them. Now, previously, from this experiment, from experiments, we can see that this has broken and this sample has not. But we really want to understand, why is this design better than this design? We want to learn mechanisms. We want to learn techniques so we can design better materials. And so we use simulation to look into mechanisms that we cannot see in the experiment. And so this is an example of a simulation that is using the same boundary conditions as the experiments, using the same materials, and also the same weight. And you can see here the very unique mechanism. So natural materials are composed of this very unique architecture, and it's made up of a lot of interfaces. And these interfaces create a maze that prevents cracks from growing. And so it's basically trapping the crack from going through the sample, enhancing its mechanical properties. So previously, what I talked about is about natural materials. And natural materials has served as a great inspiration on designing materials. But now, with advances in computation, advances in artificial intelligence, it is now possible to generate designs better than nature's. But there are many challenges. Take, for instance, the structure shown here, full of cracks. And our goal is to figure out, where do we place two different materials? Let's just say at our disposal, we only have two different materials shown on the left. One is very stiff and one is very soft. Where do we spatially place these two different materials to enhance the structure's mechanical properties? Now, in this very simple 2D system, made up of very few elements, the number of combinations in this system surpasses the number of atoms in the universe, making it very expensive to compute and very difficult to design. We have developed a method to accelerate this design process using artificial intelligence. We represented materials as images, and then we trained a deep learning model to learn the features of the top performing designs. What kind of patterns do really good materials have? And from there, we're able to generate designs that are superior, that have very superior properties compared to the designs the model actually learned from. We are now applying this technology to the field of manufacturing, specifically to bring about smart 3D printers that are capable of detecting, monitoring, and self-correcting in real time to lead to high-performing 3D printed materials in the future. So in this video, we are currently printing in real time, and it's shown on the very left. And so what our machine learning model sees is on the image on the very left over there. And what you see on the right is a probability chart. So in the beginning, we are trying to detect problems while 3D printing. And currently, the red curve right there is showing us under extrusion. Under extrusion is the imperfection during printing. And so in the beginning, our model is detecting that there's a very high probability of almost 80% that there is this imperfection occurring. And once it detects this imperfection, it starts to correct it by changing, in this case, normalized flow rate. It starts to increase flow rate in order to correct this imperfection. And after it has corrected this, you can see that the probability of something becoming good quality or something having no imperfections starts to increase from 20% to above 50% chance to have higher quality. And so this is really showing that we're capable of detecting imperfections and self-correcting in real time. So in sum, in our research, we have developed a platform that integrates computation, artificial intelligence, additive manufacturing, and experimental validation to design and manufacture the next generation of materials with specific functions and desired properties for various applications. Thank you very much. Do you want me to leave this? That's right.
All right. Thank you, Grace. And I'd like to invite all of our faculty speakers today back up to the table at the front on the stage. And I think we have about 10 minutes for questions. I think I should just hand it over. I'm sure that people in the audience have questions, and if not, I have questions. But I think yours might be more interesting. So when you do ask your question, please raise your hand so we can give you the microphone so that people can hear. There are people outside of the auditorium watching as well, so please be patient and use the microphone. So first one here.
This question is for Professor DeJong. In your experiment with a centrifuge, the sample that you are studying would simulate the interaction between the structure and the soil. But the soil sample is dry. In the real environment, the soil moisture content may fluctuate. Now, how do you take care of that issue? And also, how do you define degradation in that old train overpass structure? And sometimes failures can be a tipping point.
Sorry. I'll answer the first one. We can talk about the second one after. The first one, in the centrifuge experiment, it's true that the type of soil creates a different settlement process. So we can simulate dry or wet sand. We can also simulate clay. We can also consolidate clay if you're a geotechnical engineer within the centrifuge. So we can spin for a long time and let the clay compress itself to simulate a realistic situation. So what we're trying to do then is, if we can do those different scenarios and if we can model those in a computer, then we can make the actual geology more complicated in the computer and hope to simulate that correctly. That's our trajectory or our outlook on that, yeah.
Hey, hello. This question is for Professor Abbeel. So you showed us how you can generate, fake images. And the question is that it has so much potential, in the bad hands, right? To be abused, this technology, and just by not releasing it is not sufficient. Is there some way that you can actually detect that some images or some videos are actually generated fake? Is there some way for an indicator automatically to, in this way to kind of forbid this kind of fake news to be generated?
Yeah, it's a little trickier than you might think, because it turns out the way these things are trained, there's two neural networks playing a game. One neural network is trying to generate images that look real. The other neural network is trying to detect whether things are real or not. And at convergence of the game, at the Nash equilibrium, the detector of real or not doesn't know anymore. And so it's not super straightforward to detect it at that point. To be fair, right now, usually the detectors are still a little stronger than the generators, but ultimately, as the technology progresses, at the equilibrium, there will be no way to detect it that way. So the more likely route might be something cryptographic, where you keep track of the sources of information with cryptographic signatures. And so then you still don't know if it's real or not, but you know who generated it. And so if somebody wants to maintain their reputation of generating real things, then they have to consistently do that. And then you'll know it's from that source, so I trust it, or another source, maybe you don't trust it. So that's what I think will be needed. But still a lot of research has to happen in that direction.
Back here. Hello. This question is for Grace. The question I have is, in the case of a 3D printer, you're able to actually visualize and see how things are being laid down. How do you scale this for larger scale materials and for buildings, construction, those aspects of having a fail-proof structure? Thank you.
Okay, so the question is, right now we are able to monitor for our sort of a small scale printer, and how we actually, and how do we scale it up, right? So currently we have our printer, and we are detecting different imperfections, and the imperfections may occur between the layers, so like delamination, and imperfections can happen along the layer, so like extrusion and under extrusion, over extrusion and under extrusion, and we have cameras on both the sides and also the top layer to detect these things. And so, so that's how our current setup is like. And so if we want to expand it to larger buildings, I believe that you would need to use a lot of more sensors and strain gauges and a lot more sophisticated devices in order to monitor. But I think it's possible, but I've never looked at that scale.
Back here. This question is for Professor Pieter Abbeel.
Yes.
Abbeel.
Yeah,
Okay, so I'm a tennis fan. I just wonder, with your research and the technology, do you think can help? Develop some kind of artificial intelligence software, help the kids, adult to learn tennis, because tennis become good player take like 10 years learning practice. Like one license, $100, 3 license a week, 300. So a month, like $1,000 to learn the class. So I'm really
Fix that problem for us, Peter.
What a great question. Not to mention, tennis is my favorite sport, so I'm really glad you asked this question. So I think one of the things that is becoming more and more feasible is to do pretty reliable tracking of body motion. So if somebody's making some motions, understanding exactly how they're moving. 5 years ago, there was the Kinect from Microsoft, and you could dance in front of it, and it would score you a little bit. But today, you can actually track bodies quite reliably, even from a phone. And so I think this is going to become more and more feasible. I haven't seen it for tennis specifically, but I've seen it for working out. So full disclosure, I'm actually an advisor to the company, so I have some shares, but there's a company, Onyx Fit, started by Berkeley students, and with the iPhone 10, you put it in front of you and you do exercises like squats, push-ups, all kinds of things, and it monitors your motion and gives you feedback on whether you were doing it the right way or not. It's counting how many reps you're doing. And so these things are becoming more and more feasible. So yeah, I think it'll get there, and you can just put your phone next to you and it can give you feedback rather than needing a $100, $200 an hour coach next to
you. Any more from the audience? Otherwise,
yeah, a couple more.
I can go. Professor Abbeel, in each department, this is not a technical question. Have you seen any of the new students interested in traditional electrical engineering, or everyone wants to do CS and AI?
Well, so it's a very interesting question. So within the graduate program, it's very visible, like what the interests are, because people mark it when they apply. And so when I got to Berkeley, I think out of the maybe 2,000 applicants, 300 applied for AI, and this last year might have been 1,500 or something. So it's definitely shifted a lot from other areas into AI. I wouldn't say the other areas have necessarily shrunk. It's more that it seems like all the growth is new people coming into AI, and the other areas stay pretty stable. So I don't think the other areas are shrinking. It's just the growth seems to be largely in AI, at least in the grad program interest. I I will say, yeah, it's sometimes tricky. So one of the projects we have is actually building a robot, which I didn't show here. And finding students who can do electrical circuit design is actually much harder than finding students who are into AI. Much, much harder.
One in the back of the room? Yeah. Hello. Question is for Grace. So have you thought at all about how the materials would be recyclable when you build these kinds of additive type materials?
So that is definitely a very hot topic in additive manufacturing, is how can we actually recycle these materials. Unfortunately, in my lab, we're not working in this area right now, but definitely something we're going to work on in the future to create a sustainable world. Yeah.
Thank you.
Great.
Question? Yep.
One more question.
Sure. Well, I think so. I'm Dr. Abbeel. I'm interested in your take on AI for automatic driving, cars, trucks, airplanes, and where that future lies in your perspective.
Mm-hmm. Yeah, so I think autonomous driving, one of those things where for the past 10 years, it has felt like it's going to be there next year, or at least in 2 years it'll be there, and then 10 years later, it's still not there. I think if you kind of look very carefully at the progress in AI, look at the things you see in the news, you really dissect what's going on, you'll notice that almost everything is actually in simulation in the digital world. There's very little that's actually creating value directly happening in the physical world. And the reason is that the physical world is so much less forgiving. Mistakes can be deadly, and so the level of reliability you need to achieve is just many, many, many nines. And I think it's proven really hard to get to the level of reliability, and I think much harder than most people thought. Right today, if you had some AI PhD students and you said, can you by next month do a demo around the block with a self-driving car? No problem. They'll do a demo around that one block that they set up their office at or whatever. But that doesn't give you a product that actually is usable. And I think going from this 90% to 99.999 is proving really, really hard, especially for the physical world, where it's absolutely needed.
Okay, maybe just one last question. I want to give every panelist a chance to just say, looking out, envisioning the future, 10 years from now, where do you think the forefront of your field is going to be? And we can start with Peter and come back towards Grace.
Oh, tough question. You did not prep that one.
I'm sorry. Okay, we can start with Grace. Let's start with Grace. I think she's ready to answer this question.
So in my field of design and manufacturing specifically, I'm very excited about the future in 3D printing. Currently, there are a lot of barriers to 3D printing in that you have to know computer-aided design. You have to know how to design things in the computer. And then you need to know how to use a 3D printer. And so what I envision for the future is that, so right now we have to insert a design that we have created in our computer into the 3D printer to print it. And sort of what I'm envisioning in the future is that we have an interface in 3D printers, and we tell it high-level things that we want. Perhaps we want a very lightweight material, and we want it to be a helmet. And then we tell it these high-level constraints, and then we press print, and it'll help you print this material out for your application. And so sort of that's my dream in the future.
Thank you. Matthew?
Related to the presentation I gave today, really there's a huge effort now of digitizing our infrastructure, we would say, how we manage it using digital data, how we use artificial intelligence to interpret that data and then manage better. I think that for civil engineering will take some time to do, just because embedding the kind of sensors we can quickly embed in the smaller devices is much more difficult. So I think over the 10 years that will be a big challenge that we're facing now. Yeah.
All right.
So looking back for the last 10 years of progress in AI, if you look carefully at what's been driving it, it's data, compute, and innovation. Amount of data we could never process before because we never had to compute before, and the data didn't really exist. And so when I think about, are we going to see a lot more progress in AI in the next 10 years, people will still like to innovate in the space. People will generate more data. And so the real question will become, will the compute continue to grow so we can actually do experiments that are much bigger than what we've done before? And to me, that's really the interesting question there in some sense, because I imagine there's going to be a shift from what we're doing today to becoming even more and more dependent on more and more compute. And so we'll see a shift towards AI results that use ever more compute and also more and more concentration of the ability to get those results into organizations that have the compute resources to run those experiments.
All right, excellent. Please join me in thanking our faculty panel. So if you would like to see what the next generation of engineers is up to, I encourage you to drop by Jacobs Hall, which is across the street, which is hosting an open house with hands-on activities for the visitors. And I wanted to thank you all once again, alumni and families, for joining us today. And please enjoy the rest of your stay here during the homecoming weekend. And go Bears!